Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss approximating solutions to boundary value problems. So in this introductory topic, we will be describing what will be covered in the next few topics, specifically approximating solutions to boundary value problems. We will review how a boundary value problem differs from an initial value problem. We'll describe Dirichlet and Neumann boundary conditions. We'll give a description of linear ordinary differential equations, and we'll introduce the following two techniques we will investigate. Now, in your calculus course, you have been introduced to both initial value problems and boundary value problems. And we've already looked at approximating solutions to initial value problems. In fact, we've covered the whole gambit. First order, higher order, systems of first order, systems of higher order. However, now we're going to look at boundary value problems. Now, a second order boundary value problems includes a second order differential equation and two conditions. But now these conditions will be at two different points. Now, if we're dealing with boundary conditions, generally we're dealing with a function of space, not time. And so we're going to be looking for a function u of x as opposed to a function y of a time variable t. Now, the constraints or conditions will be provided at two specific points, and we will represent these points by x equals a and a second at x equals b. A and b are two different points in space. Now, the conditions for a boundary value problem can include fixed or Dirichlet conditions, that is where we specify the value of the function at a point. But you'll remember from initial value problems, not only can we specify the value at a point, we can also specify the derivative at a point. And for a boundary value problem, specifying the derivative is said to be a Neumann condition. Now, the most common boundary conditions are fixed or Dirichlet boundary conditions. And so this says that the solution u at a is some specified value u sub a. Similarly, the boundary condition at the other end at b will be some specified value u sub b. Generally, we tend to think of a being less than b. So here we are specifying the value of the solution at two different points. Alternatively, we may specify the derivative at one of the two boundary points. We're going to choose a in this example. So instead of specifying the value of the function or the solution at a, instead we will specify the derivative at a. Of course, we can also do this at the point x equals b. Now, such a condition is described as being a Neumann boundary condition. One such case is where the derivative is specified to be 0 at a boundary point. This indicates an insulated boundary. So if the derivative at one of the boundaries is 0, that indicates that the system is insulated at that point. A non-zero derivative at a boundary point may model a system that dissipates power, for example, at a known rate. Now, why does a zero derivative imply an insulated boundary? Well, suppose your hand is 10 centimeters from a block of ice. If, of course, you move your hand closer to that block of ice, you expect it to get colder. On the other hand, if your hand is 10 centimeters away from a source of heat, again, if you move your hand closer to that source of heat, you expect it to get warmer or very hot, potentially. However, if your hand is 10 centimeters away from an insulated wall, you don't expect the temperature to change significantly if you move your hand closer to the wall. Indeed, if the temperature did change, for example, your hand was getting cooler as you were moving towards the wall, you would claim that that wall is in fact not insulated, but rather you'd say it's cooler or warmer than the ambient temperature where your hand is currently 10 centimeters away from that wall. Just to give an example of an insulated boundary, I always claimed that my boots that I wore in the winter, specifically mucklucks, were well insulated. So consequently, one time I decided to actually test this out. I left my mucklucks in the garage when it was -20. I then put them on. Now, normally one would think that if boots were sitting in an ambient temperature of -20, that when you put them on, that your feet would almost very quickly freeze. However, these were indeed well-insulated boots, and so consequently, when I put them on, even though the temperature of all of the material was indeed -20, the rate of transfer of energy to the boot was exceptionally slow, and my feet were still reasonably comfortable. Now, a second-order linear ordinary differential equation is one that is linear in the unknown function and its derivatives. Consequently, the coefficients and the right-hand side can be functions of x even in this case, but it must be a linear combination of functions of x of the unknown function u, its first and second derivatives, and this must be equated to a function of x, which we normally call the forcing function. Now, if the forcing function, or right-hand side, is 0, we call it a homogeneous linear ODE. You may recall from linear algebra, if you have an equation that is linear and the right-hand side or constant is 0, we call it a homogeneous equation. Now, if the coefficients of u and its derivatives are constant, we call it a linear ODE with constant coefficients. Note again that a linear ODE with constant coefficients need not have a forcing function that is constant. So the forcing function can nevertheless still be a function of x. It is just that the coefficients of u, its derivative, and second derivative are all constant. And of course, we can have a homogeneous linear ODE with constant coefficients. Now, recall in calculus, the only problems you are able to easily solve are those with constant coefficients. So here we have a linear homogeneous ODE with constant coefficients. We would find the corresponding characteristic polynomial, and the roots of that polynomial would provide us with the exponents of the exponential function, which would then provide us with a solution. Consequently, if the roots are complex and not real, then we also will introduce sinusoidal behavior in the solution. This is, of course, due to Euler's identity. Now, however, if an ODE is not a linear ODE, once again, due to the implicit function theorem, we can generally, almost always, rewrite the ODE in terms of the second derivative of the unknown function being a function of x, u of x, and its derivative. Now, the first technique we're looking at, the shooting method, it's going to work on an arbitrary second-order differential equation. On the other hand, the finite difference method we will look at next only works for linear ODEs. However, the technique that we are going to look at for linear ODEs, specifically the finite difference technique, it's actually also going to be used later on in approximating solutions to partial differential equations. So we're going to introduce the idea for boundary value problems, and then we will use that idea in subsequent techniques for partial differential equations, such as specifically the Laplace equation, the heat conduction diffusion equation, and the wave equation. Following this topic, you now have an overview as to the ideas that will be covered in this subsection. You understand the difference between Dirichlet and Neumann boundary conditions, as well as the concept of what an insulated boundary condition is. You are now also aware of the two techniques we will consider, the shooting method and the finite difference method. Finally, you understand the definitions of linear ODEs and linear ODEs with constant coefficients, as well as the concept of a homogeneous linear ODE. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!